Right. So we have the people in charge of this, Vangmay, Taka, Zihang, Hongxu, and Benjamin. You are the lecturers for this round. So who is going first to take care of the first part of the slides? Okay, Vangmay.
So hello everyone, today's topic is SFT, ICL, and scaling laws. So let's start with an overview first of what these three terms are. So as we discussed previously, that when we pre-train a model, right, it is essentially just a glorified autocomplete LLM. Because in the development of LLMs, they go to three stages. Where there is pre-training, fine-tuning, and post-training. Now, let's dive into why do we need two more stages after pre-training? Because LLMs are language models, and by definition, language models, they're just supposed to predict the next word. So let's say that I have a pre-trained LLM over here. How do I?
We can kind of see at the bottom with that. With the mouse.
Oh, yeah. So let's say I have a pre-trained LLM and I ask it, can you tell me about WING.NUS? So since it is essentially just predicting the next word over and over again in a auto-regressive manner, it will just say what it is. But this is not really the ideal response. It is just completing my sentence, right? So now what we must do is we need to align it to responses that humans would prefer. So ideally I would want a model that when I ask it, can you tell me about NUS, it will give me a more detailed answer that okay, NUS is a university in Singapore, and not just answer my question with another question. Right. So this is done using a process called supervised fine-tuning. It is the process of training a pre-trained model further on labeled dataset of input-output pairs. Now, how do we do it? We firstly look at our task. So let's say that we want summaries, right? So our training dataset would consider of X to be long articles and Y would be summaries. Then if we want, let's say, named entity recognition, then X would be sentences and Y would be a list of nouns and entities. Similarly, if we want answers to questions, our Y would be like a human-like response to the questions, which would be considered as gold standard. So the objective function of in fine-tuning is called maximum likelihood estimate. What it essentially is doing, it is conditioning the model so that its outputs are more likely to prefer the outputs as mentioned in the training data set. Yeah, this is the equation for it. So if you see over here, it is essentially just increasing the log probability of Y given X. So in this case, X can be the question and Y can be the answer. And given enough training examples, a model will learn how to answer these questions.
Use a trash icon.
Oh, thank you. So a mental model to differentiate between SFT and RAG is that SFT is about learning new behaviors. It is a parametric method. So SFT can teach an LLM how to answer medical questions with the same skill and language as a doctor. Meanwhile, RAG is about providing knowledge. It is a non-parametric method. It ensures that LLM has access to the latest medical research to base its answer on. Now moving on to ICL. ICL refers to the ability of LLM to learn and generalize from examples at the inference time. By inference time, I mean the moment when you are asking it questions. It is again a non-parametric method. It first came out in the paper called Language Models Are Few Short Learners, where they found out that if you scale up an LM, basically it means if you train it on more data and add more parameters to it, LLMs they gain emergent abilities. These are abilities that you didn't train the model to do specifically, but somehow the model figured out how to do it. Also, this paper gave rise to the art of prompt engineering because two main works are that people realize that if you give a model examples within the prompt itself, the model will realize how to do that task. Secondly, it also gave rise to chain of thought prompting. Chain of thought prompting is a method which, let's say, you ask the model to think step by step. This method was found to have reduced hallucinations in a lot of cases. Secondly, model scaling. Scaling is just increasing the model's size, data, and compute to improve its performance. Scaling laws allow us to estimate how loss decreases predictably as the model compute and data increase. So there's this equation where Ln is the loss function, n is the size of a model in terms of parameters, tokens, or the compute available to it, and alpha is just a scaling exponent. They predict the returns from larger models. They are used to estimate that what would happen if I assign more compute to my model or if I increase the number of tokens it can handle. So let's move on to the first technique, supervised fine tuning. So from a RAG perspective, we know that RAG provides external knowledge, but models may hallucinate or ignore retrieval. RAG also has no way to figure out if a retrieved document has factual information. We did discuss about this in last 2 weeks. So SFT alone, on the other hand, SFT is not enough to guarantee grounding in the retrieved evidence. So we need some sort of synergy between RAG for knowledge and SFT for behavior alignment. So moving on to the first paper, I found this paper called RAFT, which adapting language models to domain-specific RAG. So the problem they talked about was that retrieved documents might be imperfect, and LLMs can get distracted by factually incorrect information in a document. Pre-trained LLMs, on the other hand, they lack domain specificity. And because LLMs aren't trained to decide when to use retrieve data and when to not, this can cause a lot of problems in a RAG system which suppose has incorrect or factually inaccurate documents. So what RAFT does is it utilizes a novel structure for data. It does fine tuning using question answer pairs while also putting the model in a situation where it has to refer to incorrect documents. So for every data in this fine tuning process, there's a query which is just our answer. That's just our answer. And sorry, I said query is an answer. No, query is a question. Then A star signifies our answer. The answer is in chain of thought style, as mentioned previously. It traces the reasoning of the LLM. And then there are a set of documents that are retrieved from the retriever itself. Now for every entry, there are two kinds of model present. One is the golden document from which the answer is based on, and we know that this golden document is factually accurate, and rest they are inaccurate documents that are called distractors. So what this paper specifically does is that they take a fraction p, and for this p amount of training examples, they retain the golden document in the query, and for 1 minus p proportion of the data set, they remove the golden document, and then they conduct their fine tuning. The rationale behind this is that now the model will be conditioned on understanding whether to include the data from the document or not, and will be able to somehow judge whether the model is relevant or not. So what they observed was that RAF actually improved the performance of RAG for all specialized domains, and also including a reasoning chain instead of just a simple answer, allowed to guide the model and enrich its understanding of the documents provided to it by the retriever. So one key insight from this paper was that data definitely matters. Data definitely matters when doing supervised fine tuning. So just a quick check to make sure everyone is understanding. What if they didn't remove the golden document from the entry? Anyone?
What do you guys think? How do you have?
Maybe there wouldn't be enough space to include the instructors.
Yeah. So that way the model won't understand that when I should refer to the documents provided and when I should not. And another one, what if I increase the value of P? Can that cause some issues?
Maybe like if these supervised and it may not learn to pick the right information at all.
Yeah, exactly. So now we move on to the next paper, which is robust fine tuning for RAG against retrieval defects. So again, the problem as stated previously was that effectiveness of RAG systems is bottlenecked by the reliability of the components. If your retriever is weak, the RAG system is weak because the LLM is not getting good quality documents. And also performance of RAG system is also dependent on the quality of the retrieved documents. Let's say that I put vague and inaccurate documents in a RAG and I say that, okay, this should be accurate enough, but obviously it won't be. So their strategy was that they found out these bottlenecks and then they tried to fine tune against these bottlenecks to make sure that the LLM is reliable enough, robust enough to ignore these bottlenecks in a way. So these bottlenecks are noisy documents. Let's say I ask which album features the song Time by Pink Floyd, but in this scenario, the RAG system might just return a general overview of the band itself. Also, irrelevant documents, let's say that it retrieves in this scenario another document by Nirvana. I wouldn't want a document by Nirvana when I'm asking it about Pink Floyd, right? Also, there are counterfactual documents which might have inaccurate information. So what they are trying to do is, let's look at this figure. So these are the questions that I just showed. So firstly, they want to train the LLM on detecting defects. So as you can see over here, that it should be able to recognize that when a document helps to answer the question, when the document is possibly relevant but does not help to answer the question. And it should also be able to recognize that when it should be confident enough to say that a document contains incorrect information. That's pretty crucial. That's pretty crucial to differentiate from the truth from the false. So defect detection, sorry, I didn't cover the second. The utility extraction task is just that let's say that there's a document that does not have enough data, that does not have enough information, but it still has some information. We ideally want to maximize the amount of information the LLM is able to extract from the document, because let's say that there's a very niche topic which has not a lot of information about it. So in those scenarios, we want the LLM to be as efficient as possible. So task one, it aims to train the LLM to identify whether each retrieved document contributes to the user's query or not. So in this scenario, the data is structured like this, such that there are documents. Yeah, there are like documents given to it, and it has to figure out the answer, and also be able to classify which one helps the question and which is possibly relevant but does not help answer the question. Then in task 2, it is a very simple task of just figuring out, of extracting knowledge from a document without needing extra pre-processing steps. So they figured out that using an exact matching measurement, they found out that robust fine-tuning framework was able to outperform most of the current methods. Next, for special mention, I also found this paper called Fine-Tune RAG, which again is tried to train the model by giving one document which was correct and one document which was fictitious, which had false information in it, and they conditioned the model to basically ignore the conditional probability of the model which has false document and only prioritize the correct document. Bonus, I also found some bonus papers that, for example, FedRAG, which is a modular framework used for fine-tuning plus RAG systems. Because the problem they found was that there are frameworks that allow you to make RAG, like you can find these resources in Hugging Face, LangChain, but none of them allow you to also fine-tune your model on a specialized domain. All of the current libraries that allow you to build RAG, they are just based on API calling. Also, fine-tuning is quite compute heavy still, because these models are big, so they take a lot of time in training. So there's this technique called low rank adaptation of large language models. What it does is that instead of fine-tuning all the weights, right, it will figure out the specific weights that it needs to change, and it will change them as efficiently as possible. Basically, you are minimizing the number of weights that you need to change so that the computations required for this process is decreased.
Okay, so just quickly, yeah, go ahead.
Yeah, sure. So I have a question. For the previous slide, when they freeze the model weights, are they freezing layer by layer or yeah.
No, not exactly layer by layer. It's just that so is this linear algebra thing called a low rank representation of a matrix? Like even I myself don't know about that, but it gives you an idea of what weights are important and what weights are not important. So it is not specifically layer by layer. It's not like layer 1 should get freeze, layer 2 should get freeze. Yeah, it really depends on the use case. So it can be like first node from layer 1 gets freeze, third node from layer 2 freeze, like that.
Okay, so we probably want a more accurate description of LoRa. So I'd like to ask all our graduate students who have done some work with LoRa or know the mathematical basis to try to explain LoRa a little better, so all of us can benefit.
Yeah, sure. Maybe I can have a try.
Okay, yeah, can you speak up a little bit?
Sure. Yeah. Hi everyone, my name is Cecil. I studied NLP. So I've literally never have experiment with LoRa, but I knew a little bit about it. So please correct me if there's anything wrong. So LoRa means that we have a model and it's fixed and it's freeze, and the LoRa means that we want to add something into the representation such that it can be very well adapted to the downstream task. And by learning it, it's like we do a low rank mapping from one embedding to the internal one, and then we map it back to the original embedding such that that adaptation can be done in a very parameter efficient. So we just add something. So yes, it's a very high level overview, and I welcome further insights.
Okay,
Yeah, if I could add on to that. From what I know, I also don't have a complete understanding that. So like how low rank adaptation works is, let's say you have an 8x6 matrix. So in the full matrix, that would be 8 times 6, which is like 48 values, right? But what if you just represented that matrix in terms of the 6 and the 8 values that, like, you can multiply the one-dimensional matrices to get that first matrix. So in that way, you don't have to store all those like 48 values, but you can just store like a smaller representation. Yeah, that's my understanding of how the LoRa works.
Okay, did everyone get Indra and Yisong's points? Right, so in linear algebra, you have a square or a rectangular matrix, as Indra was saying. And it can be the result of a matrix multiplication between two smaller matrices. So Indra was saying, for example, we usually give these mathematical names like U and V, right? So we think of a column vector and a row vector. When you multiply these two together, you can get a single scalar if you multiply one direction, or you can get a matrix, right, by multiplying the other direction, right? Because matrix multiplication is not symmetrical, right? So in many ways, like Indra was saying, you can get away with a small number of coefficients that when you multiply them together, get the entire matrix back out. So this is what Yisong meant by a down projection, right? So you use a small amount of coefficients that's smaller than the total number of entries in a matrix in order to represent the entire matrix. Okay, so in many ways, it's very similar to like JPEG compression if you think about it. So if you've ever loaded a JPEG and you turn down the resolution very low, it gets very pixelated. But basically, that's just saving some small amount of information for the average color in, let's say, an 8x8 pixel grid, right? And as you turn up the resolution, you get more resolution, you get more finer details. So when Indra was talking about multiplying, let's say, a column vector by a row vector, you could instead multiply two column vectors by two row vectors, and you would get double the number of coefficients, and you would still get the same output, meaning the same 6x8. Okay, or you could multiply 3 rows by 3 columns and still get 6x8. Okay, so it depends on how much information you want to throw at the problem. Okay, so there are lots of approximation problems that are like this. So if you take our linear algebra course, especially, I hope all the graduate students have done this. Okay, the linear algebra course, there's the pinnacle of linear algebra, which is singular value decomposition. I'm mixing up my acronyms. SVD, and that is exactly teaching this technique. Okay, the idea that you can decompose two things into smaller matrices, and that you calculate along the diagonal, you get the eigenvectors of most importance at the top going down the diagonal. Okay, so you can look these up in ChatGPT if you want. They are important, but the most important thing is you have an approximate method that can scale variably from full resolution of the matrix down to a very approximate number. Okay, and so when you do LoRa or any of these approximation techniques, it is basically trying to approximate the full grid of information with less, right? Okay, so when Yisong says I'm adding information, right, it's to say that I already have a full matrix. Okay, that is the frozen model of a foundation model. But when I'm tuning, it means I don't want to preserve those values. I want those values to change. But if I tune it the normal way, which is SFT, then I have to change all of those numbers, all n times m. Okay, so what instead I want to do is do what Indra said, which is I want to just change one row m, one row n, but not n times m. I want to just tune m plus n. Okay, and because it's a low rank approximation, when I multiply that m times that n, I get out a low rank approximation of m times n. It's not a very good approximation, but it is an approximation. So what you do with this matrix that comes from that multiplication is you add it to your existing frozen matrix, right? Some values will go up because the addition is positive. Some values will go down because what you're adding is a negative number, and you get a permutation of the original matrix. Does that make sense to everyone? Okay. Anyone would like to add more detail to that? Because I'm also giving sort of a hand-wavy argument.
Yeah, I come from a non-technical background. My understanding of how this works, LoRa and QLoRa, is that when you do fine tuning, it's like performing plastic surgery. So you're modifying the eyeball. But when you do Q-LoRa or LoRa, you're putting on a pair of spectacles. So the spectacles don't modify the eyeball, but it does interact with the eyeball to give you clearer vision.
That's exactly right. It's an additive, like Zihang says, we're not touching the model. We're just putting a pair of spectacles in front of it, right? Or a LASIK or whatever in front of it, right? And it can be additive or subtractive because the model weights can change up or down. The important part is you could give it through glasses, which is a good idea. It's exactly the same as sort of like additive supervised fine tuning, but we're trying to get away with less information. So that is why LoRa is efficient, is because the LO stands for low rank, right? LOR, right? So that's low rank, which means I use very few parameters to change a lot of things at once, right? Does that make sense? So it's like having a master dial for changing a whole bunch of parameters in them. Okay. All right, yeah, let's continue.
Yeah, so one another technique is also called quantization, because because SFT requires a lot of computational resources. This and this proportion arises from the inference stage of the model, because you are getting its outputs, comparing it to the loss function, then updating the weights. So the solution is that weights of the models are usually stored in float 32 format. So what if we store them in a smaller representation like int 8? So that means in 8-bit integers. Using this lowers the cost of mathematical operations that we have to perform on the models and saves in some inference time. Yeah, and that's it for my section. Let's move on to in-context learning.
Okay, let's thank our speaker. Hongxu or Zihang, are you guys here?
Yeah, hi, Professor. Can you hear me?
Yes. Zihang, you're on remote, then you can take over the screen.
Yeah. Can you see my screen?
Yes.
Okay. Hi everyone. I'm Zihang, and today the topic for me and Hongxu in this section is in-context learning. Here is the overview of my part. We will focus on three things. First, what is in-context learning? And second, how demonstration shapes in-context learning, including demonstration selection, format, and ordering. And third, we will ask why in-context learning works, and we will look through two views, a Bayesian kernel regression view and a gradient descent as inference view. And finally, we will close with some takeaways and open questions. Now let's start with the basics. What is the in-context learning, and how does it compare to the supervised fine-tuning? As mentioned before, the first formal definition of in-context learning appear in the paper Language Model are Few-Shot Learners by OpenAI team. They define in-context learning as a paradigm that allows language models to learn tasks given only a few examples in the form of demonstration. And we can look at the picture. We just place K demonstration that follows a simple template, then add a new query in the same format. The frozen model completes the pattern with positive, no gradient steps and no weight updates, just conditioning on the examples. So how does it compare to the supervised fine-tuning? With in-context learning, we gain 0 or few-shot adaptabilities. We can iterate quickly and switch tasks without retraining. And we can avoid catastrophe forgetting because we never touch the weight. And we can steer behavior directly by editing the prompt. However, the trade-offs are also real. We are limited by context length, and inference cost grows as we add more demonstrations. And performance can be sensitive to which examples we pick, and how we format them, and in what order we present them. It also tends to be high variance and more brittle out of distribution than a strong SFT model. Now, someone might be wondering, since the prompt is our program, how do we choose the demonstration well? And in this part, I will introduce a paper that revisits how to select demonstration for in-context learning. The author starts from a simple question. What makes one set of demos better than another? Their key conjecture is that ICL performance rises and falls with how well the model understands the test input itself. To verify this assumption, they partially shuffle words in the test input. When the input is shuffled, hence harder to understand, accuracy jumps greatly in both one-shot and three-shot settings, which supports the conjecture. And building on this, they propose a method called COME, conditional entropy. This method can be stacked above any selected demo methods like best matching 25 and top K. The mathematical forms are very straightforward, just searching for demos that minimize the difference of the cross entropy between prompts and demos. And empirically, this recipe is simple and effective. On the plot, we can see that adding COME consistently improves over the underlying candidate pools, whether those pools came from random, best matching, or top K. And in both datasets, the compute overhead is just a few extra forward passes for re-ranking. Therefore, we can conclude that effective demos are those that can improve the model's understanding of the test inputs. Then in this part, I will introduce two papers that study how prompt formatting affects in-context learning. They take a very controlled approach, keep the content identical and vary only the surface form. They define a format space that arranges from tiny token level tweaks like changing labels, separators, spacing, and casing, and to full template styles such as plain text, Markdown, or JSON. Then they test across classification, reasoning, code, and translation tasks. So what do they find? First, format matters a lot. Simply switching formats can move accuracy dramatically. There is no universally best format. Larger models like GPT-4 are more robust, but still sensitive. Second, the sensitivity persists even when we add more short, switch to extraction tuned models, or change families of models. Preferences also don't transfer reliably. Maybe what we can do in the real life practice is to standardize template, run a small format sweep, and keep the winner format. Then let's see the plot on the right side first. Even with the exact same demos, simply permuting their orders can swing accuracy a lot. And the best order changes by instance and by models. Some study tries to find the optimal ordering by relying on an extra domain in-domain dataset. But a paper from ACL 2024 introduces demo, a dataset-free example ordering method. It is a two-stage ordering framework. In stage one, they score many permutations using what they call content-free entropy. They remove the actual test input and replace it with a meaningless token like mask. And for each permutation, they compute an entropy. Low entropy means the order is coherent under the model, even without a real input. Then they keep only the low entropy orders and also ensure the label distribution is balanced. This gives a small short list of reasonable orders that are cheap to consider. And in stage two, for the actual input XT, they measure the influence of each candidate order, defined as how much that order increases the model's confidence on the correct label compared with using the order alone. And intuitively, stage 1 finds order that look reasonable in general. And stage 2 finds the order that helps input most. But the limit is that two metrics of content-free entropy and influence are designed for classification tasks. So further adjustments are required if we want to generalize them to the other tasks. And next, let's talk about why in-context learning works. Here, we just summarize the state of two leading views, not walking through formal math proofs. So you can click the paper links on the slide if you are curious about math details. So the first one is Bayesian and kernel regression view. Some works view ICL as the model doing implicit Bayesian inference over a latent concept. As we add more in-context examples, it will smoothly move into a kernel regression behavior. The prediction becomes a similarity weighting average of the demo labels, with the kernel induced by the model's representations or attention. However, there are some limitations to this view. The Bayesian kernel stories tell us what the effective computation looks like, but not how transformers implement it step by step. Then it also leans on exchangeability, while real language models are order sensitive, as we mentioned before. And it under-explains multi-step reasoning or planning style behavior. The second one is gradient descent as inference view. Some works argues that pre-trained transformers can simulate one or a few gradient steps over the demos. During inference, attention applies data-dependent updates, effectively meta gradients. So the models behaves as if it had lightly fine-tuned on the demos, but without changing store weight. Two concrete results make the story more compelling. First, several papers shows an attention gradient descent duality. In simplified or linear attention forms, the contribution of demo tokens to the next layer can be written just like a parameter update on a square error objective. And second, and there is an exact weight conversion result. In linearized attention transformers, the entire effect of a prompt can be converted into explicit weight deltas that, when applied, can reproduce the same output as prompting. And for standard softmax attention, an approximate conversion can yield similar behaviors. However, from this view, some issues still remain, and much of the clean theory use synthetic tasks or models trained specifically for ICL. When we test natural pre-trained language models, ICL and true gradient descent can diverge. Also, some commonly used similarity metrics turn out to be fragile. Re-evaluations shows that even untrained transformers can look similar under those metrics. So here are takeaways and open questions for my part today. The output score or probability distribution of LLM plays an important role in demo selection or ordering. And there is no universally best format in ICL. And can we predict the best format for a new instance without search? Then for K demonstrations, the size of search space of permutations is K factorial. How to find the best orders efficiently is also a challenging question. And also some studies have taken a preliminary steps to explain ICL. Most of them are partial and limited to simple tasks or models. And more relevant research is needed in the future. That's all from me today, and thank you.
Yeah, that's our speaker. Okay, I realized we didn't thank Vangmay for his section, so let's thank Vangmay. So Are we clear about all the takeaways that Zihang put up on the screen here? So what do we mean by output score probability distribution plays an important role in demo selection and ordering? Who can decode that in some way to help us understand what that means? Anyone online or in the room? Okay, like what this slide that Zihang is showing, what's the premise of the problem that came up here? Why is ordering important?
Because the order of them was actually doing stuff.
Right, so Jiaying is answering, the ordering of the answers that in a multiple choice question or things like this can influence the result. And in fact, here we're talking about demonstration, right? So the demonstration ordering also affects things. Okay, yeah, go ahead.
Can I clarify, like when they put the examples, the demonstrations, and then the mask? So when they send this as an input, the probability distribution refers to the how the large language model wants to predict the next word. So is the entropy like a measure of how confident they are of the next word?
Entropy is, I think, what the model decides to output for the next token or the next the selection of the answer, right? So in the example on the colorful examples in the top left of the blue figure, right? I think Zihang is showing 4 demonstrations. Okay, and they're just colors, right? So depending on the ordering of the demonstrations, you get a different result. Okay, and that doesn't make a lot of sense to us, right? It doesn't really matter which example you see first, right? They're all examples of the underlying phenomenon. They're just supposed to help you solve a new problem, right? So the problem is being given to you, but you're also given demonstrations about how to do this task, right? But it turns out that ordering happens, right? So what is being done here in the top part of the diagram is to say, measure the effect of the demonstrations order, right? So let's say you put the blue one first, that's in the top row. Then maybe you find that it almost always selects the right answer, okay? So if you put the blue one at the back as row 4, maybe it always selects the wrong answer, okay? So then you can use this information to, when you do your actual test, to try to figure out where to put the demonstrations to influence how to interpret the results of the model. That makes sense. You can recalibrate what the model's output is. If let's say you knew you did something similar to the last row where you put the good example last and you know it's usually wrong, then you would say, okay, well, I put it in the wrong place, so I'm not going to trust the results of the language model as much as I put the blue result, which I know is better, at the top. So how do you want to elaborate?
Yeah, I think you are right.
Okay, so just make it clear from stage 1 and stage 2, right? So we have 2 formulas here, right?
Yeah.
So can you explain these formulas for us?
The first one is just they call content-free atrophy, which means when we replace the true input by a meaningless token, and they predict the next token, the loss of the next token, just like what is the good demonstration is that they can't adjust the distribution before we see the true test input. And stage 2 is that in this after the stage 1, the candidate order in which one it minimizes the influence, which means that it can steer the model's behavior largely in the when we give in the true input.
Okay, are we all following that? We understand what that means? Okay, so the first step is to sort of calibrate how much effect the ordering has, because you're giving it a meaningless task. You're saying, do something, but I'm not going to tell you what, or do blank, right? So it's a no-op. But you know the ordering matters in the demonstration, so you're trying to calibrate how much is all, right? And then in the second part, you are using that to try to tune the results to be best as possible, right? So that you can see the bottom argmax is very similar to the top part, right? So the top part is just normal cross entropy. If you've seen a formula like that, it should be fairly familiar to you, therefore like log p. Yeah, go ahead.
Am I correct to say that so in the first part where you basically switch the orders, right? You still also use like entropy to measure like how much entropy or not there was in a particular order. And then what I understand entropy to mean is like C is the context, and then Y is the probability of the stuff that comes after, right? So I mean, after you do the log and everything, if you have like it's very sure that you would have I don't know if it's high or low entropy, but one of them would mean that it's very sure, and one of them would mean that the model is not very sure about the next thing to predict. So yeah, so to summarize the question, what I'm asking is, in the first part when you switch the orders, are you also checking entropy? Yeah.
Yes, I think that's implied by the formula, because you're taking a summation over all the outputs y. Yeah. So yes.
Okay.
All right. It's sort of like, you know, when you take a scale, electronic scale, and you put nothing on it and you calibrate it, and it says like -4 grams or whatever, and then you hit the tare button, right, which is like saying zero it out, right? So that's what the first stage is doing, is measuring the discrepancy between something that's meaningless, that shouldn't have any difference. Like if you give 4 demonstrations, no matter which permutation, you should get the same results, right?
Yes.
Because you don't actually get that, because the ordering of the demonstrations actually matters even for a nonsensical task. You want to measure it and recalibrate it, so when you do stage 2 for a task that matters, you can get the appropriate output, right? Okay, so that's how I understand what's going on these 2 parts, right? Stage 1 is to measure the influence of the ordering, and then stage 2 is to use that influence to maximize that the correct prediction is out. Okay, so there are a couple of things on these slides that are important. How is one, so Zihang also put on the general channel another paper that is by another student in our group in WING that looks at ordering. There's another paper that he wrote that's about format, which I think Zihang also showed in HAL number 2 or number 1, that formatting also makes a difference, right? If you ask for a result in a particular format, sometimes the results get better, sometimes they get worse. And so we need to, again, try to calibrate that and to know for a particular question, what's the best way to ask for that information, right? Okay. So let's go on. I think Hongxu has the next part, right?
Yes, Professor.
Okay, so you can share screen.
Yeah.
Thank you.
Okay.
So those of you online, please also interact with us. You know, either write something in the chat or use the Slack to comment on some of the discussion questions that Xiaoming has put up as well.
Okay, can you guys see the screen sharing?
Yes.
Okay, so I'm going to start my introduction. So I'm going to introduce the ICL, also the LLM, mechanistic explainability. And since that the mechanics explainability is they totally base their explainability on mathematical reductions, but not like running the model and collect the model states and doing some sort of analysis. So I think that is some sort of elegant explainability methods. So I dedicate a whole section introducing that method. And so I'm going to introduce some backgrounds. There are something that we take for granted, such as the large language model is just a black box taking tokens as inputs and produce the logics. And if we provide examples in context, it improves model performance. And in a mathematical definition, it is reducing the per token loss. And what we don't know is that the detailed steps of producing that logics and how LLM learn from the examples. Is that from copying from the previous examples or doing some sort of like the fuzzy or tolerant matching? And well, there are already lots of explainability methods, such as the gradient-based ones. That is if we calculate the partial derivatives to some input or some intermediate model states, or probing, such as we train external classifiers on model states, or there are also some what I think is solid work that is game theory based, such as the Shapley value. And well, what I think about them is that they are all feature attribution methods. They are like analyzing which input or which intermediate model state stand for, or their individual importance of producing the final model prediction. And I'm going to make a metaphor. That is, if we treat the LLM as a complex binary program, and doing explainability is like doing some sort of decompilation of that program, like doing object dump or something like the IDA. And this kind of feature attribution explainability methods is like for each CPU clock, we collect the variable or register states, but we still don't know the exact program code or the assembly instructions of our model. And that is what mechanism explainability aim to solve. That is revealing the execution process of neural language models. And so I'm going to focus on Anthropic's mechanism interpretability research. They have two fundamental papers, a mathematical framework for transformer circuits and in-context learning and induction tests. And first, I'm going to introduce their key conclusions. That is, in terms of model operation, they find that the attention operation is independent, additive, composable, acting as a read-write operation on a portion of the contextualized word embeddings, or they also call them the residual stream. And for different kind of transformer architectures, such as starting from the single layer transformers and ending to large transformers, the large language models that we use for production, the paradigm of doing in-context learning is quite similar. That is like copying a previous token and contribute to the presence of that token in the upcoming index of token. Well, I think the original Anthropic research paper is some sort of obscure. We cannot, if you try to read the original paper, maybe it is because the way of the object of their proposal of the paper is to provide some sort of astonishment. So they focus more on like giving some sort of conclusions, but the mathematical reductions and the and the motivations of giving their methods is some sort of hard to understand. So I'm going to adopt a very different elaboration logic from the original paper. And I will also use my own drawings to intuitively explain the complex matrix operations. And please bear in mind that I will have a lot of different colors while they stand for some sort of correspondence relationship. So we just start from some simple linear algebra concepts. That is something maybe we tend to ignore. That is a metric. One of the basic definitions of matrices is that it characterizes a mapping from a one-dimension vector to a one-dimension vector. Well, it is like what I have drawn below. That is, if we treat the matrix as a set of column vectors, we apply matrix multiplication on the left side. So each vector will be independently mapped, and there won't be any sort of like element perturbations between these vectors. So if we want to perform a purely matrix to matrix mapping, a completely mapping, it is required that we multiply it on both sides. That is, we do the column-wise perturbations, we also do the row-wise perturbations. And that is the intention of giving the tensor notation that is given by the anthropic researchers. Well, the definition is that a tensor W is defined as x left multiplied with W and right multiplied with A. Well, that tensor notation, if you are familiar with some sort of linear algebra library such as NumPy or PyTorch, is like it's like doing we unsqueeze the first two dimensions, and then we multiply it with with W, and it causes a four-dimensional tensor. But maybe you should just focus on the detailed explanation. That is, a tensor notation denotes multiplying on both sides, and one side is if we treat the matrix X as column vectors, one side is doing the column-wise mapping, and the other side is doing the column perturbations, like in what I have drawn in the figure below. And that is like we multiply each column vector, and then we do the column perturbations while these vectors form the overall result. Does anyone have any questions about what I have explained so far?
Questions? Are we all clear about what's going on? Because we know matrix multiplication is asymmetric, right? Left and right.
Yeah, I see. So I'm just go on. So that tensor notation has some axioms such as the multiplication, the associativity, the distributivity, and the identity. And maybe we should bear this in mind. That is because in the following sections, they will be very critical to our mathematical inductions. And there are also some LLM preliminaries. In the right figure, I've drawn a complete process of the multi-head attention of transformers. That is, it first projected into query key value vectors, and it is right multiplied with the attention scores, and then it is multiplied with the output projection matrices. Well, similar to what they have explained before, is that if we dive into the formulation of the attention score, we will see that the query and the key projection vectors, they are multiplied together, forming a larger low rank matrix. We call it the WQK. And also, if we focus on the output projection matrix, we will find that attention is independent and additive. That is, the multi-head attention is mathematically equal to adding each attention sequentially. Maybe that is some sort of computational inefficient, but it will foster our understanding of the model execution. Well, if we apply the tensor notation on the LLM attention, we will find that, like the figure I have drawn below, there are two kind of circuits. One is that what is used to derive the attention scores, and it is like two residual streams. They are multiplied together with the low rank matrix. And what another circuit is that, maybe you can see that in the figure before, by applying the axioms we have introduced before, we will find that there will also be another low rank matrix that is multiplied by the value and output projection matrix is also a low rank matrix. That means that for the input residual stream, we will first do some sort of per token mappings denoted by the WOV and do some token perturbations. And that is like, since it is a extremely low rank matrix, that is like we have a linear subspace of the residual stream and we have it read and written. And then we do some sort of attention perturbations, causing the final write operation to the residual stream. So there are two kinds of matrices, also two kinds of circuits, the QK circuits and the OA circuits. And if we start from the one hot input token vectors, and we have our analysis all the way down to the logics, we will find the below tensor notations. And by also applying these kind of axioms, we will find that there are also two kind of paths. The direct path is that it goes through the residual connections. It is like a bigram language model, where the attention head parts, they are added together, and there are also the two kinds of circuits. One is the query key circuits, and another is the output value circuits. And well, by explaining the expanded query key output value circuits, we will find that there is two kind of more expanded tensor notation. That is, they start from the one hot token vectors, they come along all the way and to the logics. Well, the expanded OA circuits and QK circuits are two kinds of mappings. Well, the OA circuits is a mapping from one hot token vector to a logic vector with the same shape. Well, it denotes what an attended individual input token contributes to the final logics. And the expanded QK circuits is a mapping from two individual one hot token vectors, and it produces a scalar attention score. It is a bilinear mapping. It denotes what two attended tokens contribute to an attention score entry. And what I have to mention is that these two mappings are broadcastable. That is, we can also apply the mapping on a set of one hot input vectors, or two sets of one hot input vectors, and they will produce a set of output logics, also a matrix of scores. Well, the thrilling fact until now is that the one-layer model is fully understandable. It is like what I have made in the model decompilation metaphor. It's like getting the function names and function descriptions in a decompiled binary program. And so I have a question, that is, given the fact that the two vectors that is being mapped by the circuit's low rank matrices are one hot, are there any direct ways to attribute these two extremely low rank matrices? Anyone has any clues?
So let's take a quick understanding. Who understands what a circuit is?
I understand a bit, but maybe it's not the same, strictly the same definition as,
Okay, so Hongxu, maybe you can tell us what you mean by a circuit, because some people here are not very clear about what a circuit is.
Okay, I see. So that maybe a circuit is like a kind of data flow from something that we are interested to another set of things that we are interested. For example, the OA circuits, we can see that it is multiplied by the embedding, the output value projection matrix, and the unembedding. It is like a way, maybe I should start drawing. It is like a way starting from the input one hot token vectors and directly to the output logics. And also the QK circuits, that is like a way starting from the input one hot token vectors, and we should bear in mind there are two sets of input vectors, and all the way directly to the attention scores. And maybe my personal understanding is that they propose the circuits to make the execution process of transformer clearer. That is, there are some sort of direct data flows. That is, what I mean by direct data flows is that it is derived by a single large matrix multiplications, starting from some sort of features that we observe easily, and deriving some sort of final model outputs or model intermediate states that we are interested. So am I clear?
Okay, and are we more clear after Hongxu's understanding? Can anyone paraphrase that to just say one or two sentences? Try your best. Anyone?
I think Shamal mentioned something.
Yeah, so Shamal had a really good explanation for that. So I don't know whether you looked at the Zoom chat. So I think Shamal, if you have a second, maybe you can read out what he said.
Okay. Let's see.
So basically, when we think of circuits, yeah, no worries.
Yeah.
The point of the circuit is to be able to attribute, right? It's to go back and say, from some factors, I know where this result comes from, right? Like you want to say the result 48 was attributed to 6 times 8 and not 24 times 2, for example, right? So you need to know where that result came from, right? So we're trying to trace back to the origin components, either the expanded output value circuit, right? So we would explain what the output value is, where did it originate from, and then very key circuit is to tell us, okay, what was the query and the key that got multiplied together to get the output, right? So if you can trace this through the transformer, then you can know exactly where some result came from, right? So when we talk about attribution, those are very important aspects, right?
Yes. And actually, I think there is another definition of circuits that is also a requirement, is that maybe if we only do some sort of like the output attribution, maybe that is kind of indirect effects, such as if we calculate the partial derivatives from the output logits to some sort of input tokens, maybe we will still see that like the token number 1 influences the output logits of the token number n. But what they mean by circuit is that it can be directly affected. It's like the token number 1 directly multiplied by a large matrix, causing the logic effects in the token number n. Well, I see. Maybe that is something different circuits from traditional input or feature importance attribution.
Okay, did everyone understand what Hongxu meant by that? Anyone would like to paraphrase?
Okay, I have a question.
Yeah, Zihang, go ahead.
Just how, if I'm understanding correctly, the QK circuit helps attribute the output to a query and a key. Is it?
Yes, it helps attribute the formulation of the attention score, actually. It is.
Then may I ask, I don't understand a lot of things, but what is the OV circuit do then?
OV circuits is like, well, it's like starting from the, maybe I should go back to the figure I have skipped. That is, we can see that the residual stream is first left multiplied by the value projection matrix. It becomes the value vectors, and then it is multiplied it is right multiplied by the attention score matrix, and then it is again left multiplied by the output projection matrix. And through doing this kind of mathematical deduction, we can see that the WV and WO can collapse together, forming something like low rank matrix. And so what OV circuits gives us is that if we ignore the attention score, we just consider what we have done on the residual stream by the value and output vectors. It's like we are reading a subset. Since the WOV is extremely low rank, we are reading a subset from the residual stream and making some sort of processing, and we are writing back to the residual stream. And maybe I think that is what the intent for the OV circuits. So do you understand?
Thank you.
Okay.
Okay, yeah, so we should continue, but if you are not very clear about that, it's really helpful, I think, again, for all of us to really understand what the transformer is doing, be able to trace the linear algebra that's going on, because these things are actually very crucial from a technical perspective, right? Because
Yes.
although you can do all the things by forking and cloning things and fiddling with them, if you understand the math, you're at least two steps ahead of other people who can just implement, right?
Yeah, and that's why I'm going to introduce that kind of mathematical framework in detail, since I think that is very important that we just reverse engineer transformer completely. So maybe I shall answer the question myself. That is, given the fact that the mapped vectors are one hot, the two matrices, one is the OV matrix, one is the QK matrix, is that since the one hot vector can be considered the matrix multiplication of one matrix and a one hot vector can be seen as indexing a specific row or column of that vector. So if we inspect specific row or column of the always circuits, and maybe that we don't care row or column, that is just a transpose operation, we will find that what one token have on the effects of the logics. And since the cookie circuit is multiplied by two one-hot vectors, one from the left side, another from the right side. So if we inspect if we inspect a single entry of that matrix, we will see that if one token, we see token A, and another token, we see token B, appear in the inputs, what effects will they have to the attention score? And so my explanation shows that it is easy for us to attribute these low-rank matrices. And so the anthropic researchers, they made some analysis of the one-layer attention-only transformers QKOV matrices. Well, the exciting fact is that they found that most of the heads are doing some sort of copying. That is, for these heads, the QK circuits are attending to a plausibly next token, and the OV circuit is just increasing the logics of that token. Well, there are some sort of examples, such as if the token now is R, maybe it will attend to perfect, and it will increase the probability of perfect. So that is like perfect, blah, 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 R perfect. And there are also some kind of copying which has something to do with the subword tokenization of transformers, such as if the token we are seeing is C, maybe they are attending to Indy, and they are forming a person named Cindy that is subword tokenized. Well, there's another discussion, since we see that the two matrices are in shape vocab times vocab. So it is extremely large. And if we do some manual inspection on these really large matrices, it is always tiresome. So are there any good ways we utilize some sort of linear algebra knowledge to automatically make some sort of attributions on it? My hint is that we should focus on the expanded OV circuit, since it multiplies the one hot token vector on just one side. So the multiplication is simpler. Does anybody have any clue?
Okay, any questions? Okay, so I think we should go ahead.
Okay.
We need to take a short break after your section. So
Okay,
yeah,
okay, I see. So just go ahead.
yeah.
So
thanks
I'm
for the explanation so far. Yeah, continue.
yeah. So actually we can use eigenvectors to, especially for that token copying case. That is, since the eigenvector models, if a matrix multiply a vector, it will just shrink or decrease that vector in some extent, like modeled by the eigenvalues. That is, if we have the lambda that is positive, it means that some sort of linear combination of one-hot tokens increase their own probabilities after being processed by the OV circuits. So they made some eigenvalue visualizations, and they see that most of the eigenvalues are in the positive side, and most of them are real numbers. Well, if we calculate the eigenvalues of randomly initialized weights, it is like a circle. That is, a lot of eigenvalues are complex values, and they are both positive and negative. So that indicates most of the attention heads are doing some sort of copy. So if we expand to the two-layer attention-only transformer, we just apply the tensor notation once again, and we get the following deductions. That is, there are a lot of individual attention heads which is equal to the one-layer transformer since there are residual links, and there are also some kind of virtual attention heads that is a composition of two attention heads. The attention score matrices and the output value projection matrices are multiplied together. And there are some sort of characteristics. First is that even though the attention operation gets repeated, it results in exponentially complicated behavior. That means that if the model has 4 or 8 or 16 layers, maybe it is too hard for us to do some sort of linear algebra analysis. And what we should bear in mind is that layer 2 attention scores is not so simple. The layer 1 attention score, what I have explained before, can be derived directly from the one-hot token vectors, while the layer 2 attention vectors, the layer 2 attention matrices are derived from the residual stream after the first layer. So what's wrong with the layer 2 attention scores? That is because layer 2 attention may involve operation on the residual stream. And the residual stream contains two parts, one directly from the model embedding, and another comes from the results of the layer 1 attention heads. So it might be too complex for us to analyze it. So are there any tools to solve it? Actually, we can still need the tensor notations. That is because the tensor notations makes it easier to do some sort of deductions on complex linear algebra operations. But what we should bear in mind is that the tensor notations I mentioned before, it is doing some sort of matrix to matrix mapping. Well, what we are going to do now is we are going to do two matrix to one matrix mapping. That is like the bilinear mapping, what I have introduced before, and maybe the original definition of tensor notation cannot adapt to this situation. So the authors proposed what I call trinary tensor notations. Well, the original paper's introduction maybe we should not read it. It is hard to understand. My deduction is that, like the mathematical equation on the red side, that is the way to produce the attention score of the layer 2 attention heads. That is two residual streams. They get transposed and they get multiplied together. And we can see that the token perturbation or the right multiplication matrices are put aside, and the token-wise multiplications are collapsed together. And that forms the sort of trinary tensor notation. And also the axioms such as the distributivity, what I have mentioned before, still holds true. So we can still do some sort of mathematical deductions. So if we apply the trinary tensor notations to layer 2 attention score, we will find that there will be 4 kinds of situations. One is that it is completely the same with the layer 1 attention scores. That is it starts from the word embeddings from the input layer. Well, one is that the query side comes from the first layer's attention. Another is that the key side comes from the first layer attention. And the most complicated one is that both the query and the key side comes from the layer 1 attention. And well, we have noticed that there are potential kind of compositions. That is, the layer 2 attention had reads from the layer 1 attention has outputs. maybe there are some kind of automatic discovery for compositions. That is, we can notice that there are some sort of matrix multiplications. And also from before, there are also some kind of matrix multiplications. And as what I have explained before, is that circuits are essentially matrix multiplications. So we can use some kind of like matrix norms to indicate the extent of matrix multiplications. That is, the multiplied matrices, if they have values that having relatively larger absolute values, it indicates some kind of stronger composition. And through that kind of composition analysis, the researchers found that in layer 2 transformers, most attention has dedicated to a kind of like a kind of attention function like they call the induction has. That is, for a token like the A, it attends to a token before, also A, and it increases the probability of the token after that token, that is B. Well, what they find next is that since that is a kind of V composition, that means that the value set comes from one layer 1 attention head. That is, the layer 1 attention head is just a simple attention head that moves information from the token before that token. And so the token right now can attend to the token after the former occurrence. So what I have known before is that one layer, they have such kind of generic copying behavior, while 2 layers, their copying behavior are more specific. So that explains that the larger transformer models can really learn from the in-context learning few-shot examples, even though they are out of domain. The transformers never learned it before because it is looking for the already existing tokens. So it is some kind of more robust copy. And what about larger transformers? That is the conclusions of the other paper. That is, the larger transformer also have lots of induction heads. And actually, it also dedicates a great portion of the model's in-context learning abilities. Well, the induction heads might be a little bit different, such as the fuzzy mapping, they are different languages or synonyms, that they are similar, they are close in the semantic shape, in the semantic space, or they are kind of striated induction heads, not just the token after the previous token. Well, they achieved that kind of conclusion just from the empirical support, such as the in-context learning scores, the prefix matching score, or doing some kind of knockouts that the mechanics interpretability researchers tend to do. And that is the empirical observations, such as there is a great phase change on the in-context learning score that is doing a very little window. The in-context learning ability of a model greatly improves, and in that window, also a great number of induction heads form. So that shows some kind of maybe not causal, but also statistical correlated. And also that is an example of the fuzzy mapping, that is the French version of the large. They also doing some sort of induction head attention behavior. So what does this leaves to us? That is, sometimes, even though a large transformer is complex. Maybe it have billions of parameters. It have several dozens of layers. It might still be quite simple. Maybe that aligns with the principle of ResNet. That is a model that is quite deep. Given the residual connections, most of the operations are still some simple operations starting from the input to the output. And due to the predominance of induction heads, it shows that LLM also their in-context learning abilities. Maybe they are essentially advanced copying machines. And what the limitations are that mechanism interpretability of large models are still empirical. It is not like what they have done for the 1-layer or 2-layer transformers. Maybe they cannot do the mathematical reductions. That is because it is exponentially complex. And what I think is that it is kind of degeneration to a generalized feature attribution methods that is the methods I have mentioned before, like revealing the variables of the decompiled programs. And maybe I think that is what we should focus on in future research of the mechanical interpretability of large language models. Okay, that's all of my introduction. Anyone has any questions?
I think in the interest of time, we won't have time for questions. We still have 2 sections and 20
Yeah.
minutes. So let's. We also have Kahoot. Sahej, are you guys? Yeah. Okay. So we're gonna take a 2 minutes break while Sahej sets up, and then we'll run Kahoot. So we're going to run over time. So if you need to leave after Taka section, that's fine. I know Ben has quite a lot of slides.
No, it's not.
Okay.
I cut it on my log.
Okay, but we can leave them in at Okay, so quick bathroom break and we'll start with you. And then we'll have Taka. Taka, you're online, right?
Hello, bro.
Yeah, okay, so after Kahoot, you'll run your section and then we'll round us out at hopefully it's no later than 8 o'clock. Yeah, to start. Yeah, your session.
Yeah, sure.
Thanks, Taka. So please scan the QR code. We certainly have more than 8 players, okay? I mean, at the beginning we have 20 slots, so let's make sure all of us scan and sorry for the edits because of the two coaches. I made some edits which I think are like solved in the so some edits for it one is for it the other. Yeah, it's okay. After class we can sanitize it, so there's only one left. Is that okay? We have 11. Any more takers? Everyone in Kahoot? We have more than 11 people here, that's for sure. Can we get to 20? 13, 12, 13. Okay, when we get to 15, we'll start. Okay, yeah, you can hit start. Go ahead and narrate for us.
Which method should be used for real-time and large-scale semantic search? This is a multiple choice question. So the answer is HNSW and Vamana, if I'm pronouncing it correctly. I apologize for my pronunciation. It looks like T is on the first position. What is the primary trade-off of using binary quantization for vector compression in approximate nearest neighbor search? Correct options are low memory footprint and noticeable drop in accuracy. Okay, KZ is overtaking to the first position now. For batch processing with high accuracy, which is the best approach? Sorry. Ben is overtaken and now at second position with KZ at first position. Let's see, we have 3 more questions. Okay, turbo rag is fast due to. This is a single answer question.
We have high entropy. It's like we don't remember what happened last week. You guys are not the only ones that is 0 so far.
We have Xinpeng coming into the top 5 and Pool and T on the first and second spots. 2 more questions to go. What is an essential feature of Raptor? Yes. The third, the fourth and fifth positions are changing. Let's see. Last question. What is the downside of KD tree? So KZ, Pool, and T at top 3 positions.
Rest of your resumes did not pass screening.
Okay, so this time I tried and made questions across the slides. So like if you like want to cheat in this, you have to go to like 2 to 3 different slides to get the answer.
Yeah, you did well. I think we all failed.
Yeah.
Congratulations. Yeah, let's have a hand for Sahej. Okay, Taka, we're going to go back to you. So we'll stop our screen share. And it's over to you. I don't think we're sharing, right? Yeah. So. Oh, sorry. No wonder you guys, we weren't sharing the screen. Oh my god. Taka, go ahead. At least you can share. Taka, I think you're muted. Sorry. Can you unmute? Your screen share is fine, but yeah.
Hello.
Yeah.
Yes.
all
Yeah.
good.
Sorry. Can you? Okay. So can you hear me?
Yes.
What is it? Okay. Just a moment, please. Okay. So, can you see my screen?
Yes.
Okay. Yeah. All right. Then yeah. Let me start my part. Okay. So I'm going to present about the model scaling part. So this part contains two sections. One is about LLM training perspective. Other one is LLM inferencing perspective. So first of all, I'm going to introduce scaling law. This is there's a good paper to explain this concept with empirical result. The paper is Scaling Laws for Neural Language Models, written by OpenAI researchers. So yeah, okay, what is scaling law? That is empirical rule between compute and test loss, and also dataset size and test loss, and also most importantly, a number of parameters and test loss. So what does it mean? So as we can see these three plot, we see a kind of a linear relationship in each. So left hand side, there's a okay. So vertical axis meaning the test loss during model training. Specifically, this is the cross entropy loss. And the horizontal axis is about amount of compute spent during the model training. And the middle graph is also vertical axis is the same, total loss in terms of cross entropy. And horizontal axis is a size of dataset, namely it's a number of tokens used during the model training. And right hand side is a number of parameter of the model, excluding embedding component. So yeah, how we can interpret these results? It says each compute dataset size and number of parameters show a linear relationship with test loss on a log plot, meaning that there is a power law relationship. And loss has a power law relationship with each of the three scale factors, CDN. In case of there is no bottleneck in other two factors. So meaning that if we spend more computation, then we get a lower cross entropy loss during test. And same apply for dataset size. As we increase dataset size, we get a better model, and same apply for number of parameters. And so, okay, so in this paper, also introduce interesting observations. So first of all, performance depends strongly on the number of parameters, and less impactful in terms of model shape. Yeah, in these three graphs in the top row, we see kind of a loss increase, and what we see is if we increase the percentage of feed-forward layers in the model, we see a slight, only a few, difference in terms of the test loss. And same apply, similar concept apply for the middle graph. So if we increase the number of layers, given the same number of total model parameter, we see a little bit difference. And same apply for attention head dimension. So even if we decrease or increase attention head dimension, we don't see so much difference in terms of test loss value. So which means that the number of parameter is really important in terms of the LLM training. But model shape does not so much matter. This is one observation. And the second observation is we can see bottom row two graphs. And so we see kind of a scaling row, like a linear graph, if we excluding embedding component. If we include the embedding component, scaling row, yeah, there's still kind of a linear relationship. But if we exclude the embedding component, we see more clearer, like a linear relationship. Yeah, so in that sense, so like yeah, we can say, okay, number of parameters is important, but embedding component is not so much kind of impactful in terms of like a scaling law perspective. And this is the second interesting observation. So convergence is inefficient. So what does it mean? So as we can see this graph, so okay, so if we increase the model size, we see like a significant model improvement, while number of epochs in the model training does not so much impact. So in general, in the traditional machine learning, yeah, like a neural network or even training like XGBoost or random forest, we usually train a model until validation loss converges in order to get the optimal model. But given the like a same computation budget, like running a multiple epoch is not so efficient compared to just train larger model. Like a train larger model with a fewer number of epochs is better than the training a smaller model with the many number of epochs. That is also interesting observations. And this observation tells us to what to invest given the kind of a fixed computation budget. And another interesting observation is, like scaling law actually holds across domains and different model architectures. So this graph is coming from the another paper, like scaling laws for autoregressive generative modeling. And so what we see is we see a similar kind of scaling law linear plot for not only just for language modeling, we also see image modeling or multimodal text to image or image to text, different domains. So it means this scaling law would be a kind of a universal property in when we deal with the larger scale deep learning model. And lastly, okay, so why scaling law is important? Is this just academic interest? Actually, it's not. This is practically useful kind of properties. Yeah, because it helps us to estimate return on investment. So as you know, large language model training takes so much time, so much computation cost, and also labor-intensive effort during the kind of tuning or debugging and so on. So in that sense, let's say we want to build a brand new large language model, but this will be a huge project that takes so much cost in terms of money and time. So in that sense, this scaling law properties helps us to estimate kind of a return on investment, like how much budget do we have, how much computation time we can utilize, and then what kind of, how much kind of a performance gain we could expect. So by knowing this, by scaling laws help us to estimate or project these numbers before actually starting the experiment. And we may, this concept also may help to do a kind of a design decision for model training. Like, should we train model longer time, or should we train larger models, and how much extent? And there's so many kind of decision factors, such as should we collect more data, or should we get more hardware resources instead, or given the fixed budget, and so on. So in that sense, this scaling law help us to kind of project and kind of and help clear this kind of uncertainty to make the project more kind of substantial. Yep. Okay, so far I have explained about the large language model training scaling law perspective, and second part is about inference perspective. And I'm going to introduce a paper about the inference component, that is scaling LLM test time compute optimally can be more effective than scaling model parameters. So this paper is written by Google DeepMind researchers. And okay, so first of all, let me introduce what is test time compute. So test time compute is the computation during inference, not some LLM model training. So assuming that we already have like a pre-trained large language model available, and we are going to do an inference to generate some meaningful result. But the problem statement here is okay, so what if we spend computation resource for the inferencing time, not just give a one-shot prompt and just get a prompt and just take as it is. Instead, can we say generate multiple like output from the same prompt and do some like optimal choice to pick up the best answer, for example, in order to make the inference result better. And is this effort worth investing compared to do a pre-training, spending more computation budget for pre-training? This is a kind of a problem statement of this paper. So yeah, in that sense, so when we think of test time compute, okay, we need to think of which component to invest given the fixed computation budget. And for inference time, there are two players. One is the proposer. This is left-hand side, circled by blue. Proposer is just generates a token candidate given prompt and given the pre-trained large language model. And second player is a verifier, right-hand side. This verifier is to evaluate and shortlist better tokens out of the candidates generated by proposer. So we could think these two players separately and think of how to optimize them based given the fixed computation budget and kind of a prompt provided by like a user. So okay, and in that sense, this is kind of a mathematical formulation to think of how can we derive the optimal scaling strategy given the variables. So yeah, so basically this is formula is just telling we want to find the optimal scaling strategy for test time compute given the couple of factors. First factor is about the prompt, that is Q. So maybe if we want to address the difficult prompt, we want to do some more comprehensive computation and for easier prompt, maybe we do something different. So the optimal strategy can be different depending upon the kind of a complexity or difficulty of the provided prompt. And n is a number of parameters, and the and so on. Okay, so first of all, I'm going to talk about the verifier part. Verifier is this one. So so let's say we already have a multiple a token candidate provided by proposer. So how can we pick up the a best tokens? So in this paper, there are three two approaches. First one is most simplest one, best of n, just to pick up the a best tokens. And second one is a beam search. So basically, large language model generate a token one by one sequentially, but large language model may provide generate multiple different tokens, and this beam search is to help not just only pick up the best token based on greedy algorithm. Instead, pick up the token that could be kind of promising in future. So if we take a greedy approach, we just pick up the token that has a best kind of a score. Score can be determined by reward model that I will explain next page. But anyway, let's assume we have a kind of a reward model to evaluate how much this generated token is good or bad. And beam search is just is help pick up a certain amount of token candidate. So let's say pick up top K token candidate and compute and retain a top K tokens and pick up the best one as we continue generating a token. And last one is a look ahead search. This is kind of a extension of beam search. So beam search is basically using a reward model to computing a current rewarding score. But look ahead search does more complex things like a forecast of future kind of a future score by doing some kind of a Monte Carlo simulation that require more computation though. So, but in summary, best of n is a kind of a good approach. So it's simple and it's very competitive when sufficient computation budget is available. So in terms of beam search, this is also effective for small computation budget and easier problem. But if the query is complex and getting complex and computation budget increases, then this advantage is diminishing against best of n. And look ahead search is in general, this is inferior to other two approach given the fixed computation budget. And this is because look ahead search requires kind of a Monte Carlo simulation to forecast the future reward, and that takes additional computation resource. And that's why look ahead search was inferior in this experiment. And next thing is answer aggregation. So we have a multiple answer candidate, and we want to kind of aggregate. And in general, there are two kind of rewarding model kind of a candidate. One is the outcome reward model, and another one is process reward model. And process reward model was better in this paper's experiment. So this one was taken, and we have a multiple answer candidate, and there two-stage aggregation was happening to determine the best LLM output tokens among all of candidate. So first step is stepwise aggregation. So basically just use the process reward model's prediction and to determine the like full answer score. And next step is do inter answer aggregation. And this is using a best of n weighted approach. So basically pick up the best of n, but still picking up the kind of a token in probabilistic manner. Yeah, let's say we have like a 3 token candidate, and yeah, and each candidate has a score, and based on the score, the candidate are picked up based upon probabilistic manner instead of deterministic manner. Yep. So next one is about proposer. So proposer is okay. Let's go back. So yeah, this is a player to generate a token. So there are two. Okay, so mainly three approaches are proposed. First one is parallel sampling. So this is just some pick up the different like output, and eventually pick up the best one. This provides a kind of a diversity. And the second one is a sequential revisions. So this is kind of generating a sequential token, but try kind of modify the token by the kind of a self-reflection, self-critic. And as a result of experimentation, they found that the combining both approach could be better depending upon difficulty of a problem to solve. So in this paper's experiment, they use a mass dataset to let LLM solve kind of a mathematical problem. And for easy problem, sequential revision would be a better solution. But if LLM faces difficult problems, like mix in parallel is a best approach. And I think it's because the parallel sampling provide a more diverse kind of a candidate to address the problem to find the answer. And maybe if problem is difficult, we should have like a multiple like a separate answer candidate so that we can increase the probability to have like a right answer out of the generated candidate. Yeah, so this is the last part of my presentation. So this is kind of a comparison between LLM training and inference. So this is helping us to think of which phase we should invest for given the fixed computation budget. Should we invest LLM training or inference? But actually, like test time and pre-training computation are not one-to-one interchangeable, but we still find kind of a trade-off or balancing depending upon the problem difficulty. And yeah, first thing is for easy or moderate problem with a smaller amount of inference. So increasing test time compute is more efficient. Efficient meaning that we can like solve the problem with a smaller computation in total, including both considering both pre-training computation and test time computation. But for the difficult problems to solve with a larger amount of inferencing, investing training time compute is more effective, meaning that if we want to address difficult problems by LLM, we want to make LLM much smarter by like training intensively more on large language model, like spending more kind of adding more data set or increasing a model parameter. And the difficult problem is a bit hard to solve by smaller LLM with multiple with the kind of just for inferencing. That's the observation of this paper. Yep. Yeah. Thank you so much. Yep.
Okay, that's right, Taka. So that's going to have to conclude today's session. So let's first thank all of our speakers today. So Ben has already produced the slides, but unfortunately we don't have time to hear his voice. So we just thank him for his section. As I've put in the general channel, please reserve some time to go over the notes that Ben has created for this section. And next week we'll meet, but both ITAL as well as myself, we will be out of town. So Song in the back will be helping to run the session. So those of you in W6, please check in with him earlier at 5:30 next week to make sure we have everything on target. Okay. So yeah, thanks everyone. Make sure that in next week it's actually sprint 2 already. So it means that you have to get your things done for sprint 2. For a couple of us who still haven't posted our sprint 1, you need to do that soon. Otherwise, I would chase you down with a machete or something. Okay. So I will see you guys all next week online. Okay. Take care, everyone.